please join me in welcoming Ash.
All right, so the microphone is on now. Great. All right, so let me first of all introduce myself. I'm Ash Pahwa. I think that you have already heard from Arthi my brief background. So today I'm going to talk about optimization algorithms for deep learning. So the previous talk that was given was totally management related. It was a very interesting talk, but now I'm just going to talk about something very, very technical, which is the optimization technique. So it's going to be a very different kind of a talk. So those people who were here in the previous talk, you're going to find suddenly change of topic, not only in terms of style from management to technical, but also which relates to calculus and a few other things that we are going to cover next. Okay, so again my brief bio. I am currently in, teaching courses at Caltech, and before that I have also taught a few courses here at USC as well. But my mostly background is in academia. I have been an entrepreneur before as well, and I have been doing work in the area of machine learning and deep learning. So this is the topic which I am going to talk about, which is optimization techniques. So one of the things that we use in optimization is called gradient descent, and I'm sure some of you must have at least heard about it, and I'm sure some of you may know actually quite in detail about it. So gradient descent algorithm was developed way back in 1847 by Cauchy, and for the last 170 years people have been using it, and no change has occurred, and everything was working just fine. And then suddenly came this area of deep learning. So when the deep learning area came basically about, then after that we encountered a lot of problems with the gradient descent algorithm. So then after that we introduced a whole new concept which is based on momentum, and then after that we came Nesterov momentum, AdaGrad, RMS Prop, and Adam. Adam is the latest optimization technique that is being used in deep learning. So that's what the focus is going to be. And so I'm going to show you some examples, some data. We'll optimize using gradient descent, and after that we are going to optimize the same deep learning model using Adam, and I can show you that how fast Adam is compared to gradient descent. So that is basically is the outline of my talk. So now let us start about deep learning. So we all know that deep learning is a part of machine learning, and machine learning is a part of artificial intelligence. So and deep learning basically came about from the last almost 7-8 years since we had the neural networks. Then how to use the neural networks to solve some of these problems. So that's what the focus is. If you have a simple problem of regression, then gradient descent works just fine. If you have a nice convex surface and if you want to optimize that thing, you can find the minimum point of that function very easily. So gradient descent works just fine, but when you go into the deep learning, then only we start seeing some problems, and that's what the focus is today. So first question is, what is deep learning? Deep learning is a neural network which contains more than one hidden layer. So if you have a neural network, you have an input layer, and then you have the output layer and the hidden layer. And if you have more than one hidden layer, then of course it becomes a deep learning. Now I just want to tell you that how many number of layers are there in a typical deep learning network model. If you are looking into object recognition systems that has been used in autonomous cars like Tesla, they have around 150 layers, 150 hidden layers or more, depending upon what kind of network we are talking about. So a deep learning is not only that you just add one more layer to it, it becomes deep learning. Deep learning basically comes out about when you have hundreds of layers, and then after that then when to solve these kind of problems becomes very, very difficult, and that's the reason why we don't want to use the gradient descent. Instead we are going to use many other algorithms. So, now as you can see that earlier we used to do the programming when we know what the rules are. So, suppose if we want to know what the rules are, then we used to feed in the data and we used to get the answers. This is a typical programming problem. But when we use deep learning for those applications for which we do not even know what the answers are. So, how to solve those problems? So, how to create those rules, because earlier we used to have the rules and the data, we can get the answers. But now what we do is that we take the data with the answers and then we are going to get the rules. This is what machine learning is all about, and this is what deep learning is all about. So, what we do is that we take millions of images or billions of images and we identify what that image is. So, we know what the answer is. So, we take billions of images and we say, hey, this is a cat, this is a rat, this is a mouse, this is a flower, this is a boat, and whatever those things are. So, we are taking the data along with the answers, we feed that thing in, and here comes my rule, here comes my deep learning network. And that is the way we are able to identify objects when the car is driving. When the car is driving, it can recognize all the objects, but we have to do a lot of training for that thing. So, basically that is what deep learning applications are all about. So, now if you have a simple regression problem, then in that case you have to find the minimum of the cost function, and that thing is easy. We can use the closed form solutions available for that comes from calculus, and also we can use the matrix approach, we can solve those problems. So, and we can also use gradient descent to solve a simple regression problem as well. But when you are using the neural network, there is no closed form solution available. You have no choice but to use gradient descent for the neural network deep learning problems. So, that is the reason why we have to modify our gradient descent, because the gradient descent does not work very well in a deep learning environment. So, that is what basically we are going to focus it on. Okay, so, now the gradient descent was developed by Cauchy 1847, but it was not considered to be a major invention, because at that time computers were not there. Gradient descent usually works when you have an iterative kind of a system like we have computers. So, we can solve those problems. So, Cauchy did that thing, nobody noticed that thing, and we have been using it since then, no big deal. But now when we started using deep learning problems using gradient descent, then that was the first time we said, oh my God, it is not going to work here. Okay. So, now what are we going to do? So, now we have these deep learning problems in front of us, and if we apply this old method which was developed almost 170 years back, it was not working. So, that is the reason why we came up with new ideas, and that my talk today is to summarize basically what these algorithms are. So, now let us talk about the gradient descent. Although you can use this gradient descent algorithm to solve the regression problem, but for regression, of course, we already have the closed form solutions. We do not need this thing for regression, but even if you apply this thing for regression, it works just fine. If you have a convex surface, and then which is most of the time is my error functions, I can basically find the minimum point of my function. So, in fact, the gradient descent algorithm is just one line of code, Next point of x, suppose if I want to, if I have a function which is y is equal to f x, if I want to find the minimum point where I want to find that value of x where my function value is minimum. So, I can say I will just start kind of moving that next value of my x is equal to my previous value of my x minus neta, which is my learning rate, multiplied by the derivative. So, it is just a one line code which everybody uses that thing, and everybody is kind of happy with it, and everything, it has worked just fine for 170 years. Now, suppose if you have two variables, then again it becomes x t plus 1 is equal to x t minus neta dz over dx, because you have to take the partial derivatives, and y again you can also increment. So, both of all you are incrementing x value as well as the y value, finally you are going to reach to the minimum point of your function, and this thing has worked just fine. So, now just by looking at it, when do you think that the gradient descent will stop working? when the value of my derivative is 0, if I am moving on a flat surface. And then if I have a minimum point coming up, gradient descent is not going to work, because x value will not increment. Next value of x is equal to previous value of x minus the neta, which is my learning rate, multiplied by the derivative. If it is a flat surface, derivative is 0. So, I cannot move further. Or suppose if my slope is very, very small, very, very gentle. So, in that case again we have a problem. Or if my slope is very, very gentle, it will even if I can find some slope, is going to take enormous amount of time to converge. So, neural networks takes usually long time to converge if they get stuck in an area which has a very flat surface. So, you can even see right now that that is the problem that we are going to face, that if my derivative happens to be 0 or very, very small, we cannot move forward. So, now this is the reason why my gradient descent is not going to work. Gradient descent is also not going to work in those areas where we have multiple minimum points. It can only find the first minimum and it is going to stop at that point. It will not go to the global minimum, but this problem of course can be solved by using many different initial points. So, you can finally able to get those things. So, again, but this is not a major problem. This is a major problem, that when the gradient of the error function is low, it takes a long time for the algorithm to converge, or sometimes it takes infinite amount of time if it happens to be on a, if it is going to be a 0, if it is going to be a flat surface. So, let us take this example here. Here I have a function, and this is one of the error functions that you can usually find these things in the deep learning world. Now, if this is my minimum point, here I want to go reach at, but if I start from here, I cannot move because of my gradient descent algorithm. My derivative is 0, I am stuck here forever. In fact, I can never reach at this particular point. So, now suppose if I start from here, then I can reach here, because if my surface is convex, then it works fine. This is a convex surface and works fine. But if before the convex shape basically takes shape, if there is going to be a flat region, it is not going to work. So, that is a problem for a problem of gradient descent. Gradient descent, which has been working just fine from the last 170 years, suddenly stopped working, and this is the kind of a problem that we face in deep learning. So, what should we do about it? So, now again here is a thing, you can even see the thing. Now, this is the function and this is the derivative of this function. You can see that my red is shown in red, and if my derivative is 0, I can never reach this point. So, if I start from -4 here, as you can see, even if I go through 1000 iterations, or if I go to 10,000 iterations, or I can go to 10 million iterations, my network is never going to converge. So, I am stuck there. So, here is a problem that we are trying to solve basically. Now, let us take another function. If this is my function, and if we happen to see some flat region, this is my minimum point, it is going to come later on, but if there is a flat region comes through, again I will get stuck over here. Because suppose I can give you a metaphor of a car. You are starting the car here and you are going down the hill, and here your car, suppose your car is here, you are going to say zoom, 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 and the moment you are going to come here, zoom, 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 you are never going to move forward, you are stuck over there. So, these are the type of problems that we face in deep learning. These kind of problems were not there earlier in the simple regression problems that we used to use the gradient descent. So, how to solve this problem? So, the solution for this problem is, there are many different solutions. First one is, which is called momentum based gradient descent, which I am going to talk about next, and then we have Nesterov gradient descent. Then we have stochastic gradient descent and mini batch gradient descent, and then we have AdaGrad, RMS Prop, and in the end we have Adam. And Adam usually is working fairly well these days, although Adam was actually developed in 2015, late 2015, when that paper was published. But so far nobody has found anything better than Adam so far. but don't count on it. Who knows, maybe within a matter of a year or two, somebody may also beat them as well. But that is the standard right now. Most of the people are using Adam. So now let us look into, first of all, momentum based. So there are three types of solutions available. One is called momentum based, then we have a stochastic and mini batch, then we have AdaGrad, RMS Prop, and Adam. So now what do we do for momentum? In momentum, the way we are going to move forward is not only based upon the current value of my gradient, but also the previous value of my gradient as well, and the previous value of that as well. So I am going to go, so it is just like that. If I am going to get stuck on that surface which is totally flat, the fuel I am going to use is not only the fuel I have in my tank at that time, all the fuel which is also sitting in reserve, I am going to use that fuel to move forward that thing. So that thing is called momentum. I am building a momentum that. So momentum analogy can be given this way, that suppose if I have to go in this direction, and if I ask this gentleman, which direction should I go? So he said, go in this direction. Then I asked another gentleman here, I said, which direction should I go? He said, go in that direction. Then I will just going to pick up my speed now. That is called momentum. Not only I am going to rely on one data, but another data as well. So that thing is called momentum, and that picks up the speed. So again, every single time I am moving forward towards my minimum point of my function, then I am going to pick up my speed. So what do you think happened? I am sure everybody must have seen a dog which is running, we are trying to catch a ball. The dog runs so fast that it crosses the point, then it comes back. So that is the price that we pay for momentum. But anyway, momentum algorithm is this. Here is very simple. Update is equal to new value of my update is equal to the previous value of my update multiplied by gamma. That is also one of the the hyperparameters, multiplied by neta and the derivative, and x t plus 1 is equal to x t minus update this update. So now you can see that if update 0 is 0 and update 1 is equal to gamma time update 0 plus neta multiplied by the derivative, but look at the my time 2 is going to be, if I expand the thing, it comes out to be gamma square update 0 plus gamma of my first derivative plus my second this derivative which has been computed on time t2. And similarly, you can generalize this whole thing, and as you can see that the update t is equal to it comes out to be the polynomial for my gamma. So that is basically the equation that we are going to get. So this way can solve that problem. So if I get stuck in a surface which is flat, I have now enough fuel left at that time that I can kind of ram it through, and I can just basically cross those points. And even those surfaces which have got a very which are shallow, which has got a very kind of a light gradient, is very light, I can speed much faster. So I can basically converge much faster. So one of the problems that we face in neural network is conversion. Conversion is always a problem in deep learning problems, that if you, and in fact, I just want to tell you that just a few years back, when the first time people were using the deep learning to identify the objects in an image, they have to run the training part for 3 months. Your computer is running continuously for 3 months and still it is not converging. That was the amount of time it used to take in 2010 and 2011 time frame. Then people started developing all of new ideas. So now we can converge these things. These days, if you have approximately 1 billion images which you are using it for autonomous cars, the training part usually takes 1 to 2 days. It is far better than 3 months to 2 days. So that is what these things have done. These algorithms have basically optimized the process so that we can do it within a matter of 2 days. So if you can do it within a matter of 2 days, then it is doable, but 3 months is just too long. So these are the techniques which have been used. So this is just the first technique I have talked about. So now the problem comes up. Here you can see that if I use, this is an algorithm that has been developed in R language, and again I have just changed one line of code. My gradient descent line has been just changed by one line, and suddenly, as you can see, if I start from here, I can converge very, very fast here. So, this is my ultimate point, this is my minimum point. So, I am starting from here, moving towards my minimum point, and then using only after 150,000 iterations, I can kind of converge it. But the problem, of course, which I am going to face would be that once I reach my destination, I will overshoot it. That is always the case, just like a dog which overshoots the ball whenever you are going to throw the ball there. And so, what you have to do is then those oscillations are going to start, and after a few more oscillations, you can see that you are going to converge to the minimum point. So, that is the technique that is being used. But so, now to solve this oscillation problem, there is a Russian mathematician, Nesterov. He suggested an idea, and he said that before you jump, and if the value of a gradient changes the sign, then do not jump, slow down. So, this thing is called Nesterov gradient descent, which was just kind of a slight improvement towards actually towards the momentum based gradient descent. So, basically Nesterov said that before jumping to the next, check the gradient at the next step, so that you do not have to do the kind of U-turn, you do not have to come back here, and basically find the minimum point of that function. So, Nesterov of course has gained a lot of prestige and respect in this industry. People use Nesterov momentum as well, but this was just an addition to the momentum based gradient which was being specified before. Now, the next thing is that, as you know, what is my gradient descent? My next value of my x is equal to previous value of my x minus neta divided then multiplied by my gradient. So, we talked about the gradient now. Let us talk about the learning rate. So, the learning rate can also be changed. So, the way to converge a neural network is that you start with a high learning rate, and as we are moving towards my minimum point, we slow down. So, that just like the way we do it here, as you know that this is the way the aircraft works also. A plane is flying 700 miles per hour, but once it reaches the final destination, as you can see, plane basically crawls towards the gate, and it reaches the destination. So, that is the technique that we are going to use here, that when we start, we have a very large learning rate, and as we move towards our destination, which is my minimum point which we want to find, I am going to slow down my neta. So, how to do that thing? So, that is, so one of the things we can do is we can use all kind of a mathematical functions to slow it down, but the first solution which that came out about was the AdaGrad, and AdaGrad stands for adaptive gradient. So, that is the thing that we have. So, let me just show you the mathematics. If you do not understand the math, do not worry too much about it. The conceptual idea is important, and the conceptual idea is that as we are moving towards our destination, we will keep on dividing the neta by some term which is going to be, will be growing with time. So, what number which can grow with time? So, this is the basically math that goes into it. We are going to define another function called g, and g is exponentially weighted moving average primarily plus the square of the derivative. Now, the square of a derivative is always going to be a positive number, always going to be positive. So, this number, as we move along, g will start growing, start increasing the value. If I increase the value of g, the effective value of neta will be reduced. So, my learning rate is slowing down. So, that was a very good idea that started by this concept of AdaGrad. So, now what the problem with AdaGrad is that my g became so large that my learning rate kind of comes out to be 0. It slowed down so much that instead of solving the problem, it created a problem, because I'm moving pretty fast, but as this is my destination, as I'm moving towards my destination, my learning rate will slow down, eventually it will become 0. It is never even going to reach there. So, that is the problem with AdaGrad, because the value of the g is going to increase so much that if neta becomes 0, of course, I cannot move forward. Either this becomes 0, I cannot move forward, or if neta becomes 0, I cannot move forward. So, to solve this problem, another solution was being proposed, which is called RMS Prop. RMS Prop solved the problem up to a certain extent, and here the g value will not increase continuously. So, they basically said g function is a very good idea, but we are going to increment the value of g based on exponentially weighted moving average. So, the g does not increase at a very high level, and so it kind of grows slowly, and because of that this problem was solved up to a certain extent. So, this is 2014, 2013 AdaGrad was announced, 2014 RMS Prop was announced. So, yes, people were started solving these problems up to a certain extent. Then came 2015. So, let me just move forward. Then came 2015, and the guys who built the Adam they were Kingma and Bai. Now, Kingma actually came from Europe, he is from Holland, but right now Kingma is working with Google research right now. As a matter of fact, everybody is working for Google these days, so hardly difficult to find anybody. And since Google is in the Bay Area, and Stanford University is also over there, so these professors are just going in and out of Google all the time. So, it is Stanford and Google has become primarily one thing at this time. There is not much distinction between them. So, now Kingma right now it is at Google Research, and as you know, all the researchers from Stanford are all basically going over there, and as you know, most of the people from Stanford actually go from Caltech. You know, a lot of the professors are got their PhDs from Caltech. So anyway, and now Bai is from University of Toronto. So, they introduced Adam. Now, Adam was suddenly a new idea, but was it a real new idea? Actually, it is not. It is just a combination of momentum and RMS Prop. So, they introduced, this is the math that they are showing over there, is that they have one variable MT. This is again exponentially weighted moving average, which is MT minus 1 minus beta 1 multiplied by the derivative, and they introduce another variable called Vt, which is again exponentially weighted moving average with the square of the derivative. So, derivative and the square of the derivative. So, and then they say that Wt is equal to Wt minus 1, which is nothing but my x values or my weights of my neural network, minus neta, my learning rate, multiplied by Mt divided by the under root of Vt. We take under root of Vt because we are squaring the term over here. So, might as well take an under root over here. Then we add epsilon. The reason for adding epsilon is that so that we can avoid dividing by 0. So, we add a small term to it, and this for some reason worked like a charm. It just works great for most of the deep learning applications. So, the deep learning applications are coming up in you know in the object recognition and reinforcement learning, and a whole lot of other applications are coming up these days, where you define very strange error functions. Gone are those days when we used to have a convex function for which you can find the minimum point of it very easily. Now, we get some weird shape error functions. So, now Adam was basically they started using Adam, and so now this thing usually has worked great. Now, this is basically what the Adam algorithm is again, and if you look into the final R code or any code which could be implemented either in R or it could be implemented in Python, there is not a whole lot of change. In fact, if you look at the original gradient descent and compare that thing with Adam, you see there are only 2-3 lines that have only changed, that is all, but that is all basically makes the difference. So, this is basically what the algorithm is, and then they also have to do a bias correction, which is that MT value also have to be changed here, which is after every iteration, MT hat is equal to MT divided by 1 minus beta 1 raised to the power of t, and VT also is VT divided by 1 minus beta 2 raised to the power of t. Again, these are the bias correction. I do not want to get into the mathematics of it, because this is not the right medium to show the calculus and all the math part of it. Just take my word for it that we have to do this bias correction, and that is it. So, this is basically is called a bias correction for Adam. So, now let us show you some results. I mean, the issue is this, that if Adam is better, then it should converge faster. Okay. So, now let me, I am going to run a model here, and it will again is simple written in R. I have got 3 predictor variables and 1 response variable, and then I can going to run this model. And so, I am going to show you this model as well, but here is basically the R code for that. So, there are two hyperparameters. The first one is called beta 1, other one is beta 2, and these are the standard values that are being used primarily in TensorFlow. If you use TensorFlow, and again you do not have to implement Adam by yourself. So, now when you build your deep neural network, just say optimization algorithm is Adam, that is it. It will done internally for you, but just to show you that it works fine. So, I am going to run these things. So, here are those kind of hyperparameters that are being used in TensorFlow. So, if in TensorFlow if you say that Adam is my optimization algorithms, these are the hyperparameters that are being used. So, now let us look, this is basically my Adam algorithm, which is being developed in R language. As you can see, this is the mathematics of it, and as you can see, this mathematics basically is very similar to this R code that I have. So, now I am going to run the Adam and going to compare the results. So, here are the final results. Now, let me first of all define what the problem is. The problem is that I have 3 predictor variables and 1 response variable. Now, when you run the deep learning neural network, it is always advised that you should always normalize your data. If you are not going to normalize it, you are going to take an enormous amount of time for the network to converge. So, if you are using deep learning, you should always normalize the data. So, here is my results. If my learning rate is so small and I use gradient descent, it took 100 million epochs to converge. And if I increase my learning rate to a little bit more, and it will never going to converge, because the things will just go out of control. Now, if I use Adam, I can increase my learning rate to 0.01, and within 100,000 I can converge. And I have the code. I do not have any much time, but let us see how much time is left. I can even run the code right here. I can show you this is going to be 100,000. But now, if I normalize my data, now if I use gradient descent, it took 2000 epochs to converge. But if I use Adam, it took 500, 1/4 of that. So, that shows the power of Adam. So, though I know that some of you some of you may be doing your PhD here at USC or some other institution, there is still some room left. You can still improve Adam. It is not the end of the you can still make it better. But again, lot of work is needed to make that happen. So, Adam is not the last chapter of this book. They will be coming in. So, 2015 November was the time when Adam was announced, and we are in 2019 at this time. So, we are basically 3-4 years has gone by. Nobody has figured it out so far, but I can bet on it that someone will come up with something new which is going to be better than that. So, that is where the future is. I mean, Adam is currently the most kind of optimized algorithm for the deep learning neural networks, and deep learning neural networks creates its own challenges, because my network is so complex. I have got hundreds, or I would say billions of nodes. I have got 150 layers, hidden layers, and each layer have thousands of neurons. Just imagine we have billions of neurons. So, and you can see that we are coming close to human brain. Human brain has 86 billion neurons. So that is an ordinary brain. But I'm sure people who are smarter than I am, then maybe they have even more than that. So we don't know exactly how many. That is just a hypothesis is. So that is the way the future is. Most of the very complex problems for which we don't have a closed form solution, or if we don't know how to solve these problems, that is the kind of a problem that are suitable for deep learning neural networks. So in the future, deep learning neural networks are going to solve some very, very, very complex problem for which we don't know how to solve ourselves. So and that is called artificial intelligence. Computers are becoming intelligent so that they can take the data and the final answer, feed them in, billions of these images will be fed in, and then they will figure it out all by themselves. And what exactly deep neural network is nothing but a neural network, and what the computers are computing during training time is the values of the weights and the biases. Those same weights and biases, my guess is that everybody has in their brain as well. That's the way our brain works as well. That's what, again, this is just a hypothesis. Nobody knows in detail how the brain works. So we are coming very, very close to figuring it out how the brain works. And once we know that thing, then my guess is that within the matter of 5 years to 10 years or maybe 20 years, somebody is going to walk into this room and you won't be able to tell this thing is a machine or a human being. It's going to communicate with you just like the way human being is, going to laugh with you and cry with you and just act like a human being. That's the kind of a problem that will be solved by deep learning neural networks. And these are the few of the foundations of those algorithms that is going to enable that technology to happen. Thank you. Any questions? Yes.
So, generally speaking, we say there is a tool for every problem. In this case, would you say that Adam is the one tool for every deep network problem?
Not necessarily. Adam is, you can try other algorithms as well. Sometimes it may not work very well. So Adam is not the ultimate solution for every problem. You can try the things as well. Yes.
Yeah, so I see deep neural network applications always at image processing or cell identification for those problems. So will it perform always better than other machine learning algorithms in like smaller scales, like transaction phases or fraud detection, or is deep neural network always outperform neural network?
If your problem is such that there is no closed form solution available, then in that case you can try. So again, deep learning is not used to do simple regression. If you have a simple regression problem, use simple regression algorithms which are there, and that is going to work much, much better. Deep learning is designed to solve only those problems. You can look at from that example as well, that suppose if here we are in LA, now suppose if I have to go from LA to Pasadena, then what is the best form? I can just take a simple car and drive. It does not make any sense to take my Boeing 747 and fly to Pasadena. It does not make any sense. So that is the basic analogy. Deep learning is not meant for simple problems. If you want to just go from LA to Pasadena, just drive. Yes?
How does deep learning relate to quantum computing?
I don't know much about quantum computing, so I don't know. I just don't know what the answer is. So quantum computing is a part of physics. I don't know. I'm not a physicist. So I just don't know the answer, to be very, very frank with you. Yes?
How many layers was your example? How many layers of computation?
No, this was a simple one layer neural network. Okay. So this example was that. But whether it doesn't matter whether you have 1 layer or 10 layers, you're always going to find that Adam is going to converge much faster than gradient descent. Yes?
Why did the data standardization produce such efficiency gains? And also, does the standardization affect like the outcomes of your model at all?
Yeah, you should always normalize the data when you do the neural networks, because when you are doing the neural networks, it is an iterative approach. If you normalize the data between 0 and 1, the minimum point is going to be between 0 and 1 someplace. So, you can transfer those, you can go this thing faster. But when you do the predictions, you have to unnormalize the data in the last stage. Yes.
One last question. Thank you.
I just have a probably stupid question, more of a statistician than I guess so much mathematics. I'm kind of curious as to how much overlap there's been in algorithm development in ML with like Bayesian statistics where you're solving intractable problems. I don't know if those forms. There's like a whole suite of algorithms that were designed or built to solve those kinds of problems.
There are many different problems are there for which simple solutions are available. And so, my suggestion is that do not use deep learning stuff for simple problems. It is not meant for that. Just try to find a problem for which there is no solution. One example of course would be the object identification in an image. Now, how can you program that thing? There is no way you can figure that out. But if you feed in 1 billion images and run a neural network, it will be able to figure it out. There are many other problems as well which are there, which are as complex as this one. So, use the deep learning neural network only for those problems. Okay, thank you.